Okay, so next we see theorem 2. So this time we are going to solve the equation cos x equal to cos y. The original statement doesn't exactly look like an equation, because what it says is that if x and y are two real numbers and cos x is equal to cos y, then x and y are related by an equation of this form. X is either 2n pi plus y or 2n pi minus y for some integer n. But then when we apply this result to an equation where x will play the role of a variable, so that we can do. Okay. So let's prove this. We have cos x equal to cos y. So that implies cos x minus cos y is equal to 0. So now we can use our cos A minus cos B formula. Because we have cosine, so both the factors will be sine, with a minus sign in front. Okay, so you recall that formula, we will get this minus of sine of x plus y divided by 2 times sine of x minus y divided by 2, that is equal to 0. So either sine x plus y over 2 is 0 or sine x minus y over 2 is 0 or both are 0. So this implies this is 0 or this is 0. And in this or statement, the possibility of both of them being 0 simultaneously is also included. That means in this or, and is also included. That's why it's called inclusive or. When you see some statement in mathematics which is an or statement, this type of statements are called disjunction. You have to understand that it really means this. Something or something means something or that other thing or both of them. If you want to mean exclusive or, which does not include that and case, you have to mention it separately. This or this, but not both. Something like that you have to write. Here, however, of course, that situation where both of them can be 0 is included. Now this means what? Since we already know precisely when sine becomes 0, so x plus y divided by 2. So, and what is that situation? That's when the input is an integer multiple of pi. So let me write m1 pi for some integer m1, or x minus y divided by 2 is equal to m2 pi for some integer m2. It's of course not necessary that m1 and m2 have to be equal. I mean, these are just two independent statements. They can be simultaneously true, but one of them is not depending on the other. Okay. In general, it's always better to write separate things. They may ultimately turn out to be equal, we don't know, but in general you separate them. Now if you write this thing somewhat differently, then you multiply by 2 both sides and then you subtract y from both sides. So that gives you x equal to 2m1 pi minus y for some integer m1, or from this one we will similarly get x equal to 2m2 pi plus y for some integer m2, and both these things can be simultaneously written at once like this. So this implies that x is 2 times some integer times pi plus or minus y. So actually we are writing two things, but in this notation using this plus or minus we can write it at once for some integer. So that's the proof. It's a simple thing, but it will be very helpful for solving some equations which involve cosine. There is another theorem which will tell us something similar about the tangent function, and that of course is this: if x and y are real numbers but none of them is an integer multiple of pi divided by 2. You know why? Because we are going to consider tan x and tan y, and if any one of them is an integer multiple of pi over 2, an odd integer multiple, okay, an odd integer multiple of pi over 2, say x is such a number, then tan x is undefined. That's why we need to remove those things from R. If x and y are two such real numbers, then tan x equal to tan y implies x is equal to n pi plus y. For some integer n. Actually, these theorems are telling us one side of a slightly more general statement, namely, not only is this true, that when tan x is equal to tan y, we have this, but the converse is also true. When x and y are related like this, and they are not odd integer multiples of pi over 2, then their tangent values are also equal. That, however, is very easy to verify. You just consider tan x, that will be tan n pi plus y, and then you apply tan a plus b formula. You will see that the right hand side becomes tan y. So there is actually no need to show that. It follows very easily. The converse which we are proving here of that thing is in fact slightly more complicated. It's not that easy. So let's see the proof. We have, in order to solve equations involving these things, we need both this implication and the converse. So this implies tan x minus tan y equal to 0. We don't, however, have any ready-made formula for tan x minus tan y, but we can, of course, turn this into sin and cos and then see what we get in terms of sin and cos. So if you do the manipulation here, you are going to get sin x cos y minus cos x sin y divided by cos x cos y equal to 0. So you can see that the numerator has fallen into a form which is sin, which is the expansion of sin of x minus y, cos x cos y. So the denominator already is non-zero, and this is also because x and y are different from any odd integer multiple of pi over 2. So this means that the numerator has to be equal to 0. But then you know precisely when sign becomes 0, namely when it is an integer multiple of pi for some integer n, and this implies x is equal to n pi plus y. For some integer, yeah. Alright, so now we have the three things with us. We have already seen what happens when sin x is equal to sin y, then x is n pi plus minus 1 to the power n times y for some integer n. And today we have seen what happens when cos x is equal to cos y and when tan x is equal to tan y. Now we are going to use these three results to find general solutions of trigonometric equations. That's what now we are going to do. So let's apply these things to two examples. The next coming examples, actually there are more, but today we are going to see only two. So let's see what we can do with these things. So the first example after these theorems is this. I think it's example 20, but I am not following any numbering, so I am just simply going to write example. The text simply says find the solution of an equation, some equation. What that really means is that find the general solution. If you simply see this sentence, find the solutions, you have to understand that you have to find all the solutions. That means the general solution. However, if someone is asking you to find particular solutions satisfying some condition, that's a different matter. Okay. Find the solutions of, what's the equation? Sin x is equal to minus square root of 3 divided by 2. So you know what to do if you want to use the first theorem. Namely, you have to express the right hand side of this equation as the sine of something. Now, you cannot immediately write a standard angle here and have this value as the sine of that angle, because the sine values of standard angles are never negative. By standard angles, I of course mean the angles we already have encountered in lower standards, lower classes. So let's see what we can do when we have a negative sign. Let's do a little rough work here. And again, always never forget that whenever you have any doubt regarding these trigonometric functions, you can always go back to the definitions of these things, which involves the unit circle centered at the origin. So, what is sine actually? If you put an angle in its standard position where the initial ray coincides with the positive x-axis, then the final ray, wherever it is, it's going to intersect that circle at some point. For example, for this angle, this is that point. The x coordinate of that point is defined to be the cosine value of that angle, and the y coordinate is defined to be the sine value. Y coordinate is the sine value because now we want sine. So the y coordinate, of course, here is the length of that perpendicular. In this case, I say length because it lies here and the y coordinate is positive. If the angle is larger than this and say the terminal ray of the angle in standard position lies in the second quadrant, then also the point of intersection has its y coordinate positive. So for this type of angles, of course, your sine is going to be positive. However, if your angle exceeds 180 degree and the terminal ray or terminal line now lies in the third quadrant, then the point of intersection lies below the x-axis. So here the y coordinate of that point is negative, so here sine will be negative. And there also in the fourth quadrant also sine will be negative. Now we do know one thing from lower standards, namely that sine of 60 degree is square root of 3 divided by 2, ignoring that minus sign. In radians, 60 is pi over 3. So we know this value. We also want the angle to exceed 180 degree or pi radian. So that gives us an idea. That gives us the idea of considering this angle pi and with that pi over 3. We, however, still don't know what the value actually will be. Let's see. This is how we can guess. Note that sine of, and what is pi plus pi over 3? It's 4 pi over 3. 4 pi divided by 3. So let me start with that and then I write that as pi plus pi divided by 3. Now, I have already said that I don't keep these formulas in mind. Okay, I don't try to remember them. Instead, I will simply use the expansion of sine A plus B. Sine pi cos pi over 3 plus cos pi sine pi over 3. Okay. Sine pi is 0, cos pi is minus 1. I remember, I know by heart. but still you can see if that's really true. What is the angle pi? Pi is this angle. For that angle pi, the terminal ray is simply the negative x-axis, which intersects the unit circle at that point. And we know the coordinates of that point. The x coordinate is -1, the y coordinate is 0. X coordinate by definition is cos theta, y coordinate by definition is sin theta. So cos pi is -1 and sin pi is 0. So this first term will vanish because we have 0 there. And here, because of cos pi, we will have a minus sign. In fact, so that we can see what we have done, I mean where this is going next, I am going to write one more line. Sin pi over 3, now use that value. So this becomes minus root 3 divided by 2. Hence, sin x is equal to sin 4 pi divided by 3. Thus, from theorem 1, you cannot of course write theorem 1 here because theorem 1 may mean different things in different books. You simply write thus, x is equal to, or okay, yeah, this is what we should write. Why am I simply writing thus? Thus the general solution is x equal to n pi plus -1 to the power n times that angle, where n is any integer. As you change the n, the integer n, you get different solutions. That all the solutions are contained in this expression itself. They are obtained for different values of n. Alright, now a remark about this entire thing. This is not exactly the only angle whose sine is equal to minus root 3 divided by 2. See this remark carefully, okay? Instead of choosing pi, had we chosen 3 pi, say, what would be the corresponding angle if you choose 3 pi here? 3 times 3 is 9, 9 plus 1 is 10, 10 pi divided by 3. Sine of 10 pi divided by 3 is sine of 3 pi plus pi divided by 3. So this is sine 3 pi cos pi divided by 3 plus cos 3 pi times sine pi divided by 3. Okay. Now, what is the angle 3 pi? 1 pi, 2 pi, 3 pi. So the 3 pi angle, if you write it as, if you express it as a rotation, then it's this. Like that, anti-clockwise, because the angle is positive. So this point is still minus 1 comma 0. So just like sine pi is 0, sine 3 pi is also 0. Just like cos pi is minus 1, cos 3 pi is also minus 1. So that is why this again becomes minus sine 3 pi, pi divided by 3. And this is minus root 3 over 2. So instead of using 4 pi over 3, if you use this angle, what will you get if you repeat all these things? Then your equation looks like this. Ten pi divided by 3. And from this, the general solution comes out to be this. N pi plus minus 1 to the power n times 10 pi divided by 3. Are we not getting a different general solution? I was just now saying that once you find the general solution, this expression has all the solutions. Here, however, it seems like we have found an entirely different expression because of this part. What is going on? Note that this equation actually is not one value or two values of x. Just like that, this equation also is not a single value of x. Although we see one equation, but that equation has a variable n. So what we are looking at here and here, these are sets of values. It's just that the general element has different looks. Here the general element looks like this. Here the general element looks somewhat different. These two sets are equal as sets. So for some value of n, say n1, you will get some corresponding x value. N1 pi plus minus 1 to the power n1, 10 pi divided by 3. This value, this real number, you will also find in this set for some value of n, not necessarily that, of course it won't be that value, some other integer. For some other integer n2, this with n2 in place of n will be actually equal to this. Those two sets are equal. So it does not matter which value you use here to express the elements of that set. The set after all does not change. It's like giving two different names to a single person. The names are different, but the underlying person is the same. Just like that, the set of values you see here is equal to the set of values you see here. Okay, so it does not matter what one writes here. That's the general solution. That was the remark. And it's not a mistake also. It's like the same God having different avatars. It's like that. Next, see another example. Solve. This one is very brief, just solve. Solve means find general solution. Cos x, this is almost immediate. This. because this is a standard value. We have cos x equal to 1 divided by 2. So for what value of x do you know that this value is 1 over 2? Same, pi over 3, that means 60 degree. So the general solution is, or if you want you can make it a little longer, so the general solution of the above equation is x equal to 2n pi. Recall what happens when cos x becomes equal to cos y, plus or minus y, where n varies over the set of integers. In your haste, when you are writing an exam and you are you don't have much time left, you may forget to write this. That will reduce your marks significantly because you are not saying what n is. Never forget to mention that n is an integer. N in fact is any integer. Okay, so this is the general solution. So let me just stop the video here itself. The remaining examples that we have in this section and in this chapter also, because this is the last section, we will solve in the next trigonometry video. And tomorrow also we have, tomorrow we are starting differential equations or topology. Let's start with topology tomorrow, from Mooncar's topology. So see you tomorrow with that. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.